using these tables to answer lots of questions. And so you could get questions about concavity and points of inflection, or you could get questions about asymptotes, or questions about relative extrema. Everything's on this table. All right, so let's start off with a rational function. How about something like this? Okay, let's just analyze this thing, meaning let's figure out everything. Let's fill out the whole table, and then we can answer any question we wanted to. All right, so what do? Lots of things to do here.
You have to find if where it's not.
Good, good. First thing we want to do is we want to find what's the domain of the function. So on our table, what are the values where it exists and where we can start to even look for these other features. So are there any places where this function is not defined? Say it again. Positive and negative 2. Good. And we get that from the bottom, don't we? We get on the bottom, we get x squared minus 4. And so if I set the bottom equal to 0 and solve, the two answers I get, right, the two zeros of the denominator would be, and we can just, just would look like this, wouldn't it? If I take this part, x squared equals 4, so x equals plus or minus 2. And really, it'd probably be more appropriate to do that. Those are the two values that x can't equal, right? And so that's our domain, right? So when we start to make our table, what will those amount to? You tell me, what's going on at plus and minus 2? Vertical asymptotes, and why? Good, the bottom is 0, but the top is not. Where are the zeros at the top? 3 and negative 3. And what's going on there? Say it again. Function 0. So those are just x-intercepts, or zeros of the function. Good. And that's handy. I mean, it's nice to know that, because then we got 2 points that we can easily add to our sketch that kind of anchor the sketch a little better, right? Okay, so we have vertical asymptotes there. That's good. What next? There's a couple different ways you could go with this, but whichever way you want to go. Okay, we'll do the calculus maybe, so do the derivative. Okay, so when we're going to do the derivative here, what do you talk to me about that? Recommendations. I mean, what rule do you want to use? Quotient rule is fine, that's fine. Sure, we can do that. So if we use the quotient rule, okay, so how does quotient rule go then? Bottom, good. Bottom, so x squared minus 4 times derivative of the top. Okay, so what is the derivative of the top? I've got that 2 out front, right? And then what's the derivative of x squared minus 9? 2x, so what were you going to say? 4x, good. So we get, so there's the derivative of the top, good. And we know it's minus top times derivative of the bottom. 2x. Good, all over, okay, x squared minus 4, quantity squared, very good. Okay, so then we just, now what? Yeah, we just got to combine like terms and simplify that, right? So what do we get if we do this? It's going to be kind of a mess, but let's see if we can just wade our way through this. We're going to get x, let's count the number of x cubes. How many x cubes are we getting from the first term? Well, but I mean, we get 4 if I distribute the 4x.
Yeah.
So we get 4x cubed minus 4x cubed. Everybody see that? Okay, so the x cubes, when I distribute the 2x and the negative 2 to the x squared, the x cubes will cancel, right? Okay, what about the x's? I'm going to get negative 16x, and then what about over here? I'm going to get 2x times negative 2 is negative 4, positive 36. So 36x minus 16x, 20x, okay. So I'm just trying to save a little space here. So now we've got 20x over x squared minus 4 squared. Okay. So we got to find our first derivative critical numbers. What's the importance of first derivative critical numbers? Why do we look for those? Well, okay, maybe a different question first. Where do we look for the first derivative critical numbers? Where the derivative is 0 or undefined? Okay. Now, is the first derivative, okay, so that's where we look for them. The first derivative critical numbers are those, do those tell us inflection points?
No.
What do they tell us? Okay, those are all of the potential relative extrema must occur at first derivative critical numbers, right? We could get some false alarms, but all of them have to be included in our critical numbers. So are there any places where the first derivative is undefined?
Yes.
Where?
2 and negative.
Positive and negative 2, are those critical numbers?
No,
They're not. Right, how come?
because it's in the original.
Okay, because the function is not defined there.
Yeah.
Good, so they can't be critical numbers. Okay, so there's nowhere in its domain is it undefined, okay? Where does it equal 0?
0.
At 0, so there's one critical number. So we know that f prime equals 0 at x equals 0, right? There's a critical number. Okay, now what? Second derivative. Good, second derivative.
That's dirty.
Okay, so we'll probably want to use this one right here, obviously, right, where it's simplified. All right.
It's a big complex.
What is f double prime of x? Got a quotient again. Okay, so what do we get?
2 squared to minus.
No, we gotta go V first, we just gotta do the bottom.
Okay, bottom first, good. So we start bottom
Let's go, Kendall.
times 20 minus
We need the bottom.
20x. And now, okay, now this is a little bit tougher derivative. What's the derivative of the bottom? Good, we gotta use chain rule. don't we?
2, this is minus.
Ah, good, here we go. So I get 2 times,
X squared minus 4,
good, 2 times hand to the 1 times,
2x.
good,
Ooh.
okay?
Kendall is on it.
All over, what's on the bottom?
It's squared minus.
To the what? To the 4th, good, yeah.
Clutch.
Okay, question? Question about where the 2 came from.
Yeah,
Where this 2 right here?
Squared on the outside?
Yep.
Alright.
Yep, that's it.
And now,
Okay, so now we gotta clean this up a little bit, right? On the top, let's see, what could we factor out? Because we do have some like bases here, don't we?
X
Yeah.
squared minus 4.
Okay, we can take out an x squared minus 4 to what power?
First.
To the 1st, good. So if we take out an x squared
You were close, like,
to the 1st, and what about, I guess that's about, well, we could take out a 20 too, couldn't we?
yes.
Right, we could take out a 20, let's just stick that out there.
First, yeah.
And then, what are we left with?
X squared minus 4. X minus X.
Minus, good, and then let's just kind of cross out what's gone. So that's gone, that's gone, that's gone, and that divided away, right? So I get minus 2 times 2 is 4, x times x is x squared.
Minus.
Yep.
Okay, is that right? Did I get that right?
Yeah.
Okay, questions?
Right, me.
If we just add like terms up?
What about on the bottom?
Okay, on the bottom, then we've got x squared minus 4 to the 4th. Okay, any cancellation?
Yeah.
Yeah, everybody see that? Now we can cancel like factors because, how many factors do we have on top? okay, if you count the 20, we have 3, don't we? We have 20 times the quantity x squared minus 4 times this other quantity that we'll simplify, right?
Yeah.
We'll push the like terms together. But these guys are like terms, or like factors, aren't they? And so because they're factors, we can cancel them. What's the power gonna be left on the bottom?
3.
3, okay, good.
3.
So we end up with a third power, whoops, wrong color. Okay, and so what do we end up with then? Let's see, on the top, we get our 20, and then all this stuff condenses to 4 minus 3x squared.
Wait, what?
Is that right? So I've got x squared minus 4x squared.
Ah, I see.
And then I've got, oh, negative 4, sorry,
There we
times,
go.
something like that.
Yeah.
Okay.
Yes.
Is that right? Hope I got that right. Did I get that? I think I got that right, didn't I?
Yeah, it just
Okay.
took me a minute to process it.
Then on the bottom,
Yeah.
okay, everybody agree with that?
Yes. See.
Okay, so now critical numbers of the second derivative.
What's the what?
Critical numbers of the second derivative. Where is it undefined anywhere in its domain? Positive, negative 2, but once again, not in the domain. So those are, you don't have to worry about those. What about the zeros?
No.
Might be easier to take that negative 1 out, so it
Oh,
looks
yeah.
like that. How about?
Yeah, I like that too.
So where x squared equals what? I'd have to, this would be the factor we're setting equals 0, wouldn't it?
What
Right. So if I were to solve the equation 3x squared plus 4 equals 0, tell me about that.
Square root.
Okay, I'm getting a negative square root, aren't I?
Yeah.
Right, I get 3x squared equals a negative number, and there are no real numbers for which that happens, right? And we're only looking for real number solutions here. So are there any critical numbers of the second derivative then?
No.
No, none. Okay, so we only had one critical number on the whole thing, and it was the first derivative critical number at 0. Okay, so we can maybe start to fill in our table. What about the tails? If I were to distribute that 2, it would look just like a polynomial over a polynomial, right? Now, what's the limit going to be at the tails as x approaches plus or minus infinity? If we end up with f of x equals 2x squared minus 18 over x squared minus 4. Remember the stuff we talked about last week? I don't have to do any work here.
Oh, 2.
Oh.
Okay, and what's the reason? Yeah, the limit is 2, isn't it?
Yes.
Right, the limit of the function as x approaches plus or minus infinity is going to be 2 because the polynomials are of the same order.
Yeah.
So they both go to infinity at the same rate. So then we just look at the ratio of the leading coefficients, 2 over 1.
Oh.
Right? So we don't have to do anything. We can just, by inspection, we can tell what the tails are going to do, right? And so now we have a pretty complete description. When we fill this in, we're going to know what this function looks like. Okay, so let's do this. We had our domain was all reals except we had an undefined function at -2 and +2, wasn't it? Okay. So that was undefined, and so we ended up with, what did we call those? Yeah, vertical asymptotes, good. Okay, if we take the other limits, we took the limit as x approached positive infinity or negative infinity, we got 2, right? And so that gives us a horizontal asymptote. And if we just put that structure on our graph, if we just do even just that much, that helps. We'll go back to it. That helps quite a bit.
Yeah, that's.
All right, and then we had one critical number at 0. So that means it's horizontal tangent line. Okay, and what should we do? We need to kind of, there's still some debate as to, as to what's happening. We don't know, there's lots of possibilities here, aren't there? Right, this thing could be going, it could be going like that, it could be going like that, it could be going like that, or like that. Out here, it's gotta either be going like that, or like that, right? Same over here, but we still have to pin it down a little bit. So, talk to me about that. Where do we wanna populate our table here? Where do we work on our table?
Bottom, just low as you can.
Or down as we can, sure, okay? So let's go ahead and work on the y prime. We gotta figure this out though, right? Is it a minimum or a maximum? How are we gonna do that? Say it again, test points? Okay, where were the test points? One, we could, 1 and -1. We can do it more easily though. Because when you're talking about test points, you're talking about first derivative test, right? What about, there's an easier way. We have the second derivative already calculated. The second derivative test, if the second derivative exists, the second derivative test always trumps the first derivative test, because there's only one point you have to test. So if we check the sign of the second derivative at this critical number, remember this stuff? This is a great trick. There's our second derivative factored. So if we plug in 0, what are we going to get back for a sign? We're going to get negative times positive. So the top is negative. Bottom we get negative. A negative number to an odd power. So negative over negative is
Positive.
positive. Okay, so if we get a positive second derivative, it's concave up. Remember what that makes. If we have a 0 first derivative and a positive second derivative, that's a happy function, right? So we said, so that's going to be a minimum, and that allows us to do this, doesn't it? Now we know what's going on there. Okay, we filled in that part. Okay. And then what about out here? There are no critical numbers. What do we do?
Yes.
Yeah, just a test point. All we need is 1 point, right? Just 1 point out here somewhere. What if we pick, I don't know,
3.
10 or 3, or it doesn't matter. Just something, anything would work, right? We need 1 point on the interval between 2 and infinity, right? So 1 point greater than 2, because the function is boring. It's never gonna change. Once we know what the behavior is, we got it pinned down. So if we plug 10 into our second derivative, what are we gonna get? Negative times
Positive.
positive over
Positive.
positive. Yeah, so it's gonna be
Negative.
negative overall, isn't it?
Yeah.
Right?
That's
I had 3 factors and an odd number of them were negative. So it's gonna be negative, so it's a sad function. It's gonna be, now it's concave down, but remember, I'm not gonna say it's sad because it doesn't necessarily, it's kind of a wry smile or wry frown. It's kind of doing something like that maybe, right? Get the idea? Because it's only, let me explain that. That was kind of, let me explain that. And you only get a happy or a sad function when you apply the second derivative test, because there you've got a horizontal tangent line. And so it has to be either a peak or a valley. See, there are no peaks and valleys out here. All we know is that it's concave down. So when we sketch it on our function, if it's concave down, what's the only way that fits?
Um,
You only have two, yeah, it's gonna have to be this one, isn't it?
Yeah.
Right?
Yeah.
That would be concave up. This is concave down, but it doesn't really look like it's sad there, it's just concave down.
It's just a half.
Now, there's a couple ways we could analyze this. We could certainly check a point, a test point on the other side, and that's really easy to do. Let's go ahead and do that. But then I'm gonna show you something else too, just something else we talked about, remind you of. If I evaluate this at -10, I'm gonna get negative times positive over positive, right? Because that's an x squared, right? And so I'm gonna get the same thing happening over there. I get negative second derivative, and so it's concave down. And so we know it's gonna have to look like that, don't we? Right? And now, if we wanna find out where the zeros are to anchor this thing, remember where they were?
3 and
3 and -3, so really it should have been, I should have drawn this a little differently, but we could add those points to maybe just improve our sketch a little bit. Probably not necessary though. How could we have utilized symmetry here? If I distribute the 2 on top, look at those polynomials. Remember we talked about the symmetry tests. Do you remember the symmetry tests? We said, and let me remind you about this, we said that even symmetry is the test that f of -x equals f of positive x,
C.
right? And odd symmetry is the test f of -x equals negative f of x. So we could do that, but remember where even and odd come from. Even and odd come from polynomials. Okay, we know that this symmetry is going to exist for a polynomial when all of the exponents are even, right? We know that we're going to get this odd symmetry for a polynomial when all of the exponents are odd, right? And so if we go back and look at this function, look, we just have polynomials on the top and the bottom. That's even, isn't it? Because I've got x to the 2 and x to the 0, right? So I have only even exponents on the top, so that's an even function. I have only even exponents on the bottom, so that's even. And remember that when you combine polynomials as factors, they follow the same kind of rules as sine rules. 2 evens combined, 2 even factors would make it even, 2 odd factors would make it even, and an odd and an even would make it odd, right? And so that's, in this case, that's probably more trouble than it's worth, but a lot of times you can just get an idea maybe how that could save you a lot of trouble. If you only had to sketch half of a graph and then use the symmetry to get the other half, that's pretty helpful, right? And that doesn't really show up in our textbook, and it doesn't really show up, but I just want you to be thinking about that. In the future, that's something that you'll use more. Okay, questions on that one? Okay, good. Is this starting to kind of come together?
Yeah.
Good. Okay, I want to show you another problem that you can do, but I want to show you an additional trick that's helpful, that makes this even easier. So what if we were to do another rational function? And I like this trick because it forces us to think back to some important elementary analysis and pre-calculus. Okay, so if we were, let's just focus for a second on the horizontal, or on the tail behavior of the function, right? So if we wanted to take limits here, as x approaches, let's say positive infinity to begin with. What's going to happen with this one? Okay, is it going to be, what are our 3 possibilities? We either get 0, right? And when would that happen?
If the top is bigger.
And then the bottom.
Okay, when the bottom is a bigger power than the top, we always get 0. And think why? Because remember that it's the leading terms that dominate when we go to infinity. All this other stuff doesn't even matter. We just compare the leading terms. And if the bottom one were bigger, the bottom one is getting big much, much faster, and if a fraction gets big on the bottom, it goes to zero, right? So that would be the case where we get a horizontal asymptote at zero. We just looked at one where we had the same order polynomials top and bottom, and then we just take the ratio of the leading coefficients, and this is the third type, where the top is bigger, the top is going to explode, right? And that makes the fraction big. So this fraction is gonna go to infinity. Now, we gotta figure out, is it positive or negative? We know it's gonna be infinite, and then what do we do to figure out if it was positive infinity or negative infinity? Yeah, didn't we just look at the signs of the sign rule dictated by the leading terms, right? So if we just look at the leading terms, these don't even matter. As x goes to positive infinity, I'm gonna get positive on the top and positive on the bottom, which is positive, right? So we know this is gonna be positive infinity. If we added let's just put in a plus or minus sign over here. Big eraser. If we do plus or minus, if we added a negative, if we were approaching negative infinity, I would get a negative number squared on the top, right?
Yeah.
1 times a negative number squared, and 1 times a negative number to the 1 on the bottom. What's the sign of that going to be if we look just at the leading terms? If I get positive over negative, see what I'm saying? Okay, so that's as far as we went, and that's pretty good. But there's an additional thing we can do here. Because the order of the polynomial on top is exactly 1 bigger than the polynomial on the bottom, we can do something extra. Okay, what happens if we actually divide this out? What does f of x look like? So we get to do a little polynomial division here.
Oh, goodness.
Oh yeah.
That's fantastic.
So we're going to do polynomial division. We'll look at this. I take this opportunity to review this with you because this is something you're really going to eventually have to do a lot with. So remember how this works then. Okay? And it's just like normal long division, right? How did we do this? How did we divide polynomials? Say it again.
This is a long time.
We just factor the equation.
Well, you could, in this case, you're right. Here's the thing. Well, actually, no, you can't. You can't. That doesn't factor. X squared minus 2x plus 4 doesn't factor. So you can't. It's a good idea. So we are stuck doing.
As long as you mention.
Okay, I'll give you. See if this rings a bell. Yes, ma'am.
You have to multiply the x minus 2 by x so that you can cancel out the x
Perfect.
squares.
Perfect. And what you're looking at here is you're looking at the ratio of the.
Negative.
Very good. You want to look at the ratio of the leading terms. You're asking the question: how many times does the leading term outside divide into the leading term inside? In other words, x squared over x is x. So we're going to multiply through by x, and then we'll just distribute that through. And just like normal long division with numbers, then we'll subtract, right? You always subtract with long division. So I end up with x times x is x squared. Now, a couple things you might notice here, though, that when you distribute that x through, you're going to get a polynomial from that, right?
Yes.
And so one thing that's really important to do with this, and we didn't have to worry about it this time, but you always want to leave a column in here for each power of x because you're going to be subtracting polynomials from one another. And just because the top polynomial, let's say the top polynomial was x squared plus 4, just because the top polynomial was missing an x term, doesn't mean that you're not necessarily going to be subtracting a polynomial with an x term from it, right? So you want to preserve those columns all the way through to make the subtraction easier, okay? Does that make sense what I'm saying?
Yes.
Okay, so then x minus 2 would be negative 2x. And remember that we are subtracting the whole thing. So I will always tell my Algebra 2 students to, put parentheses around that and a negative sign out front to remind you what you're doing. So then x squared minus x squared goes away. Negative 2x minus negative 2x goes away, right?
Yeah.
And then I end up with just 4 minus 0, so I drop the 4 down. Does x go into 4?
No.
No. So that is my remainder, right? And so what this ends up being then, this is equal to what? Interpret that for me. What's my answer? X, good,
Oh, yeah.
plus my remainder over my denominator, right? So x plus 4 over x minus 2. Good, okay? You know, why'd we do that? Well, here's why we did that. Now if we take our limit, let's take our limit again, okay? So we know that f of x equals x plus 4 over x minus 2. Okay, now if I take the limit of f of x as x approaches plus or minus infinity, what's going to happen to this? Okay, good, right, so this term right here is a polynomial, right?
Yeah.
I know that the bottom is getting big, and so that polynomial is doing what?
Zero.
It's going to 0, yeah. And we end up with the answer x. The limit of this function as x approaches plus or minus infinity is x. What does that mean? Well, that's consistent with what we already knew. When x is positive infinity, it's positive infinity, right?
Yeah.
When we approach negative infinity, it's negative infinity. But it tells us more than that. It tells us, well, it tells us the complexion or the behavior of the function as x goes to the tails. It's a line. It's a line with a slope of 1 and a y-intercept of 0, right? It's just y equals x. That's what we call a slant asymptote, because it is asymptotic, but it's approaching that asymptote. It's not horizontal, it's not vertical, it's slanted, right?
Just to look
Does that make sense? So if we look at our original function then, what are our asymptotes? Are there any places where the function is undefined?
2.
Okay, let's check that and make sure. Is it undefined at 2? It is, but we want to make sure, because this is one where,
Okay.
this is one where maybe, my point is it could have been a hole. If we check it at 2, what do we get on the top? We get 4 minus 4 plus 4. So yeah, it is. We don't get 0 on the top, and we do get 0 on the bottom, right? So we know right away that that's going to be a vertical asymptote at 2. So if we sketch this,
It looks like the outside.
there's a vertical asymptote. And then our slant asymptote was just the line y equals x. And so that's what we get, right?
Yeah.
Now, once again, we don't know what the function is doing in there, but out at the tails, it's going to stick to that slant asymptote, right? Make sense? Okay, so let's build our table. What? Can't remember what the function is, but x. So we said x not equal to. Okay, we got a slant asymptote. Now we have to just do a little calculus. Okay, so what's our derivative this time? How are we gonna do that?
Question?
Quotient rule, sure.
Yes.
More question rules.
Okay, so x minus 2 times,
2x
good,
Two
minus,
squared minus 2x.
times
minus
1, good,
Yes.
Okay, so if we clean that up, what are we gonna get? Let's see, on the top, if we FOIL this out, let's see, what's this gonna give us? 2x squared minus 2x minus 4x, right? Okay. Minus this.
That.
Okay, so minus x squared if we distribute the minus sign, plus 2x minus 4. Let's just combine like terms. And we get what, x squared. How many x's? Negative 4? And the 4's go away. There you go. Okay, all over. Okay. So critical numbers. Is the first derivative undefined anywhere in this domain? At 2. Okay. But is that defined? Is that in our domain? No. Remember what we said about that last week? Almost a philosophical point. Yeah, all the successive derivatives will inherit the discontinuities of their parents, right? So, sounds like a dysfunctional family of functions, I guess. But they, right? If the original is undefined someplace, then the derivative must be also. Okay. So the only place we would get critical numbers would be at the zeros of the first derivative, and if we factored it, where would those be? So if I wrote that as, if I factored out an x, where's it going to equal 0? Where's the top 0? 4 or
0.
0? Yeah.
Yes.
So there are our two first derivative critical numbers. Okay. Second derivative. So we're going to differentiate probably this guy, right? Okay. And would we even, would we probably do the second derivative if we didn't need to? If we weren't being asked about inflection points, I don't know if I would even do it. I mean, you could, but it's going to be another quotient rule problem. Not a real hard one, but it is quotient rule. And so really, do you see that we wouldn't have to? We wouldn't have to, just by, we could use the first derivative test on these points also, right?
Yeah.
Okay. It's not essential, but we're going to find all the, say we needed everything. So if we differentiate this real quick, we get bottom times derivative of the top, which is minus top times, what's derivative of the bottom?
Must be 2x minus 2.
Okay, 2 times the quantity x minus 2 times 1, right? Everybody see that? Kind of going faster if you want to get through this one. And then over, what's on the bottom?
X minus 2.
Good, x minus 2 to the fourth. Okay? Now here's another wrinkle on how you could do this. We've always factored out the common factors and then canceled with the bottom. I'll show you something tricky here. And yeah, you're welcome to do that. That's probably the preferred way of doing this. But if I see that I have common bases, what's going to happen when I do that? For example, the x minus 2's. I'm going to factor out what power of x minus 2 on the top? 1, right? And I'm going to cancel that with 1 on the bottom, aren't I?
That's correct.
So I could just do this, right? Does that make sense? As long as I'm canceling from every term on the top, I can do that. Does that make sense? Okay.
Sure. Yes.
Right? Okay. That's reasonable work to do. And then now that makes things a little bit easier on the top. Now if I just distribute and add up like terms, what am I going to get? So I'm going to get 2x squared minus 4x minus 4x. Right? And then over here, if I distribute the 2, the negative 2, I'm going to get plus 8x.
Yeah,
So look, a lot of stuff cancels. And so that cancels that, and that cancels that. The only thing left is an 8 on the top, right? Okay, so are there any critical numbers with the second derivative? Nope. And furthermore, what's the sign of the second derivative have to be everywhere?
It's cubed on the bottom.
Did I do that? Oh, it's cubed. Thank you. Yeah, there we go. Okay. So, boy, we're running out of time.
Oh, well.
Go on, you got 4 minutes left.
Oh, we can do it.
Yeah.
For Fox's sake, Fox's sake. Actually, can go with the clocks, right?
So what do we have? Critical numbers at 0 and 4?
Yes.
Yeah.
Okay.
0, 4,
And we had a vertical asymptote at 2, is that right?
yeah.
Yes.
2.
And we had a slant asymptote at, and that's hard to put on the table. Yeah, I think you just have to kind of write it up there.
SA at.
And we had a, okay, so what's the, all we need is second derivative test and we're done,
That's
right?
correct, yes.
So what do we get here? We know we have a horizontal asymptote at 4. What's the sign of the second derivative? Positive. So it's happy. What about at 0?
It's a negative.
That's sad. Okay, so we can add our stuff.
Let's go.
Well, where was my graph? Was it
Back.
back?
You lost it.
Oh, right there.
Yeah.
Good enough. So at 4, we were happy at 4, right?
Yeah.
So we got something like this, like that, right? At 0, it was sad, so we're gonna get something like that, right?
Yes, yes.
Won't it go farther up into the?
It might, but we know that at 0 is where we have to have the peak on that thing.
Oh.
Okay.
Let's go take it on.
Make sense?
Yeah.
Dude, I'm feeling today.